What's up, everyone? This is LeetCode 621 Task Scheduler. We've done this problem in Python. Now we're going to do it in C++. So I want to preface this. This problem has two solutions, really. I mean, it has various solutions, but I'm going to show two. One which is slightly less efficient, which is a max heap approach, and then one that's more optimal, which is kind of a greedy approach. I'm going to reuse parts of my Python video for where I do the explanation. The code will be in C++ that I'll show you, but I'm just going to reuse that video, so don't get too confused, but I'm just doing that because that last video took me like 30 minutes to make, and I don't really want to spend an hour talking. My mouth's starting to get a little bit dry, but so yeah, I'm going to cut to that, but first of all, we're going to go through the explanation of this problem, and then I'll cut to those basically explanations, and those explanations are really just like drawings and stuff, so illustrations. That's why I'm using that, or reusing that parts of that video. Okay, and then I'll code it up in C++. So this problem, we're given an array of CPU tasks, each labeled with letters A through Z, right? And then a number n, right? Each CPU interval can be idle or allow the completion of one task. Task can be completed in any order, but there's a constraint. There has to be a gap of at least n intervals between tasks of the same label. Return the minimum number of CPU intervals to complete the task. Right? Basically, what this problem is so n really is the gap between basically the gap between when you can use a task of the same label again. So you can see there's 3 A's, right? So if we use 1A, right, we can't for two intervals, right? We cannot use an A again. After those 2 intervals up, then we can use another A again, right? And in between these intervals, really, we can basically do nothing, right? So basically just leave it idle, meaning we're not doing anything, or we can use up another task in the meanwhile. So we could use a B up, right? Here we can't do anything because, again, the gap has to be 2, right? So we just use an A, so we can't use another A for 2 intervals. We also can't use a B because we just used B, so again, 2 intervals, right? So here, for example, we could use a B, right? Because it's been 2 intervals since we last used a B. Okay, so, and as you can see, right, that's the solution, right? You basically do an A, a B, and an idle, an A, B, and an idle. And how much total time did that take, really, for those CPU intervals? It took 1, 2, 3, 1, 2, 3. So 1, 2, 3, 4, 5, 6, 7. It took 8. Okay, right. Example 2, right? You have 2 A's, you have 2 B's, and then a C and a D, right? So you can do A, B, C. A, B, C, D, and A, B. In this case, really, the idle time really is 1. So once you use an A, you can use a B, then you can use a C, then you can use a D, right? Whatever the case. But you can just repeat a task after one other task, because the interval is so short. And yeah, I mean, there are cases where n could be 0, but I mean, that's really simple. Like most of the time, most of these, the n's going to be 1 or greater. For most of these test cases, anyways. Example 3 is 3 A's and 3 B's, right? So we use an A and a B with the idle twice because the gap has to be 3 before we can use an A again, or a B again, right? So it would look something like this. So we had A, B, idle, idle, A, B, idle, idle, A, B. Obviously, once you use all these tasks, right, we don't have to idle anymore. So we would never idle after this B, okay? So it'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? 10 CPU intervals. Okay. Now, like I said, there's 2 approaches to the problem. There's a greedy approach. There's a max heap approach. I'll show the max heap approach first. And yeah, the max heap is slightly less efficient, but I will show both because I think both are important to know. If you are in an interview, the most optimal approach. I mean, you should always know the most optimal approach, but it's possible in an interview they might ask you they might ask you to use a heap to solve this problem. So it's still good to know how to do this problem with a heap, which is what I'll show you. So I'm gonna edit this and cut to the part where I do my explanations, and then we'll come back and we'll do the coding for the max heap, and then I'll explain the other solution, right, by editing the video from my Python explanation. And then we'll come back and we'll solve this problem the most optimal way, which is the greedy approach. And we'll do that in C++, obviously. Okay? So I'll be right back. So really, the max heap approach, really, the idea is we're going to take these frequencies, right, of these letters, right? There's 3 A's. There's 2 B's, there's 1 C and 1 D. Okay. And we're going to add those into a max heap. Okay. Now the max heap will just have the frequencies. I just added the letters here just for the sake of you understanding what these numbers are referring to. But the max heap will just have the frequencies, okay? So the idea behind the approach with the max heap is we have to wait after we use a certain task, right? We have to wait whatever n we have to wait n intervals, right? So the idea is we're gonna start with the most frequent letters, right? So first of all, we're gonna handle this 3, right? So what we're going to do is we're gonna have a heap, and then we're gonna have a queue, and the idea is we're gonna use up the most frequent letter first, right? So we're gonna basically take this here, right? We're gonna decrease it by 1, right? Because we're gonna use one of the A's, right? So we want to decrease it by 1. And when we use this A, right? When we use this A, we're basically going to add. We're gonna add this into the queue, right? So we're gonna do 2, right? And we're gonna have a pair, right? We're gonna and the 2 because we're gonna reuse this eventually again. But the idea really is this, okay? We're gonna take this A and we're gonna use it up, right? So we're gonna have 2 A's left over. So we're gonna put 2 into the queue, right? For this position, like I said, it's a pair. And then in this position, it's going to be the time, right? So initially our time is just 1, right? Right, because we're starting at 1. So we're going to do 1 plus whatever n is, 3. So we're going to do 3. And that would give us what? 4. Okay? So what does this tell you? It tells you at time equals 4, we can actually use this A again, right? So we're going to we'll just do this. Boom, boom. Time equals 4. Right, we're at t equals 1. Right, now let's go to t equals 2. This is not in the queue, right? Because we removed it and this is not in the heap because we removed it and put it in the queue. So now at t equals 2, what are we going to do? Well, we're going to use a b. So we're going to do 1. So we're going to subtract by 1, right? So it'd be 1. And the t is 2, so 2 plus 3 is 5. Right? This would not be in our heap anymore. So when we go t equals 3, right, none of these are 3. We're going to take this. And the idea is that we're basically going to use up these tasks, right? As we go. Now, let's say we get to a spot where t is equal to 4. Whoops. It's kind of hard to, whatever. Let me just cross this out. So when t equals 4, what we're going to basically do is we're going to basically take this, remove it from our queue, and put it back into the heap, because now we've basically freed up our A's, so we can use it again, right? So we're basically, so kind of the point of the queue is basically, it's like a placeholder for tasks that we can't currently use because we have to wait some set amount of time, right? Now, if we have a case where the queue has stuff in it, but the heap has nothing in it, we would just idle, right? That would be a case where we just idle. So we wouldn't really do anything. But then, at some point, right, the time would come where we could actually take stuff from the queue and put it back into the heap, right? So, so basically the point at which we don't have anything left over, basically at what point would we break out of the program? Well, if we have nothing in the heap, and really the point where we would have nothing in the heap is basically when the task frequency reaches 0, meaning we have 0 tasks left to do, right? So if there's nothing in the heap, and when it's 0, obviously it's not going to be in the heap anymore because we would remove it. But the point is when all these tasks basically reach 0, meaning when we use all the tasks up, we have nothing left over. So when the heap is empty and the queue is empty, it means that we used up all our tasks, and we're not waiting on any task to free up. Meaning we know for sure now, because these are both empty, that we've handled every single task possible that we can handle. In which case, because the queue is empty and because the heap is empty, we're done. Okay? Okay, now that we have a general understanding of how we're going to do this with the max heap, right? We're going to basically start to implement this. But as you can see in our input, right, we have our tasks, but we don't know the frequency. So we actually have to count how many times does A show up, B show up. Now, like I said, like the actual task doesn't really matter. But we're going to use a hash map just because we need to actually count how many times each individual label shows up, right? But in terms of like we're mapping A to 3, B to 3, for example, 1. Let's say B was 2 or whatever. These keys don't really matter, but we need to actually get the proper values, which is why we're going to just map this using hash map, right? So we're basically going to sort by frequency, and then, well, we don't actually have to sort by frequency because we're using max heap, right? But that's kind of the point of the heap. It'll do our sorting of frequencies for us, but we need to actually get the frequencies, right? So we're going to use a hash map for that. So we're going to use a hash map for that. So we're going to say unordered map, right? Char int, we're just going to call it count, and we're going to say for char t and tasks, right? Let me write my code cleanly. This is only a one-liner, so we're not going to use brackets. So we're going to say count tt plus, okay? Right? And this is basically our max heap. This is our priority queue, right? So we're going to say int, say max heap. Okay, so we're going to say auto. Remember, we basically have the task and then the count, right? I'm going to map that count. Let's say max heap dot push count, right? So what we're doing here is we're iterating through our hash map. We don't actually care about the task. We only care about the count, right? Like our values. So for each task, whatever value it's mapped to, we're going to take that value and push it into the max heap, right? So here we're just iterating through the hash map, and we're pushing the actual values for whatever label we're looking at, the frequency, right? We're taking the frequency for any particular label. We're just adding that to the max heap. Okay. Now after that, right, we need to initialize our time. Initially, it's just 0, right? Let me just go back here really quick, right? So we're basically setting this up right now, okay? And now we need to handle the queue, right? So we're gonna say the queue, which is what, right? Remember, the queue really is a pair. The first one is just the remaining count. The second one is just the available time, okay? And so we're gonna say queue pair, both integers. We're just gonna call it cooldown, okay? Now in this cooldown, right, what is gonna happen? We're gonna use up something from the heap, subtract by 1 that value, and we're gonna add that to the queue with the timer for when it should be finished cooking, metaphorically speaking. And when it's done, right, we can basically take this and put it back into the heap, right? That's kind of the gist of this solution, right? So we're gonna have a while loop, and we're gonna basically say while the max heap is not empty, or the cooldown is not empty, we have stuff to handle, right? So in that case, we're going to do initially, right, we're going to add time by increase the timer. So in the first iteration, right, time is going to be equal to 1, which makes sense, right? So first of all, what are we going to do? Okay, let's check. Is the max heap empty, right? If it's not, then what do we have to do? Well, we have to take that most frequent value, right? So we're going to say int count, right? We're going to say max heap dot top, right? Right. We're going to get that count. And I just remembered in that Python video, we're doing the whole negative thing because there's no max heap in Python. So we only have min heap. So we set the values to negative so that we pop the max value. That's not really the case in C++. So don't get confused by that. Right. So we don't have to do any of that any of those shenanigans in C++. But yeah, in Python, it's a little bit weird. So we're going to basically look at take whatever's at the top of the max heap, right? That's our count. And remember, when we take that, what do we have to do, right? Well, first of all, we need to actually pop it. Okay. And we need to decrease it by 1. Okay. So basically, we're taking this, popping it out of the heap, decreasing this by 1, and then what? We need to put it into the queue, right? So we decrease by 1, we popped it, right? And actually, before we even put it into the queue, it could be the case that like, let's say we have nothing left, but we have this. If this was 1, when we decrease it and pop it from the queue, if it's 0, we actually don't want to, we don't have anything to put into the queue, right? So we actually need to do a check first that once we decrease it, is that basically, is count greater than 0, right? Because if it is, then we can put it into the queue. Because if it's 0, it means we handle all of our tasks, right? So we don't have to do anything with it, right? So I'm going to say if count is greater than 0, right? Then we want to do cooldown.push, and again, it's a pair, right? We're going to say count and then time plus n, right? Okay, go back to this picture in case you want to pause. And this is just an example. Like, this is not, I'm not using any particular example from here, from any of these examples. It's just theoretical, but I'm just showing you the picture. Okay. So we handle our max heap, right? We basically pop from the max heap, decrease it, put it into our queue. When we're done with that, we need to look at our queue, right? Because it could be the case where maybe we already have, at any particular point, maybe we already have something in our queue and it's done cooking, so we want to put it back into the heap. So we have to do that check after this, okay? So let's look at our cooldown. So we're going to say, basically, if task cooldown is finished, put task back into max heap, right? So we're going to say if the cooldown is not empty, and the cooldown.front.second, right? It's time, right? Basically, if the cooldown's not empty, and we're going to peek at the second value, or we're going to peek at this value, if this is equals to whatever time is, it means it's done cooking, right? I hope you don't mind me saying done cooking. I know it's a little informal, but I'm just trying to make sure you understand, right? So basically, whenever the cooldown is finished, meaning the cooldown is equal to the time, or when the available time is equals to time, it means basically we can remove the value from our queue and put it back into the heap, right? So we're gonna say max heap.push, right? Cooldown.front first, right? And remember, the first value is actually the task frequency left over, right? So if we have 3 A's, this here is basically, we have 2 A's left. So we're going to take this and put it back into the heap. And again, this is just to illustrate, obviously in our heap, we don't actually have these pairs, right? D, C, B, A, because these don't actually matter. I'm just doing that so just for sake of like explanation and simplicity of you visualizing how this works. But really, these are just numbers in the heap, right, that we have, right? So we're taking this number that's ready to be used again and putting it back into the heap. Okay. So when we do that, we want to basically remove this from the queue. Boom. And I believe that's it. That is our algorithm. We're going to run this. Run this. There you go. Right. So yeah, we're basically counting up this stuff with the frequencies and setting up the max heap, the priority queue, and basically this is where our how we algorithmically handle the max heap in the queue. Okay, so yeah, that's the max heap approach. Okay, it's n log k, I think, or k. Well, when we have to set up it's O of n because we have to traverse through the task, right, to actually count the frequencies and stuff. But then we have to set up the heap, which is log k. So I believe this heap approach is O n log k. Now the next approach I'm going to show you is O of n, right? So it's a little more optimal, but it's a little bit I don't know if it's slightly more complicated, but I'll do my best to explain it. I mean, the Python video I think was decent enough, so shouldn't have any issues. But yeah, we're gonna go to the optimal greedy approach now. So the gist of it is, really, right, when we have an example like this, right, we can build out what our intervals should look like, right? Because we can use so here we have 1, 2, 3, 4. We have 5 A's, right? Remember, we're going to use the most frequent elements first because we want to have the minimum number of CPU intervals, right? So obviously it stands to reason you want to use the most frequent tasks first. You want to handle the most frequent task first because, well, like I said, you don't want to make your intervals too long, right? Because if we use a B first and then a C, right? Well, it's going to be kind of weird at that point because we have an A and then we have to wait if we're using it. Because we have to use all these tasks up, right? So why would you handle the less frequent ones first? Because then when you handle these, you just have to do a bunch of waiting, and you can't do anything. Whereas if you use the most frequent ones first, you have an A here, and you have to do a bunch of waiting, but hey, you can use the other tasks like a B or a C here, right? That's why you want to use the most frequent task first. Okay, so the gist here is you'll notice a few things, okay? So when we use our most frequent tasks, right? We have basically these groups here, right? Right? Like we have a group here, 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 and then we have an A, right? And so we can kind of formulaically build how we can basically account for the minimum number of CPU intervals, given that we can kind of structure it like this, okay? So the idea is this, okay? We're going to take the max frequency and subtract by 1, okay? The max frequency. So the max frequency really is how many groups do we have, right? So if A is 5 and we do 5 minus 1, we're going to have 4, which makes sense because we have 4 groups, right? We have a group here, we have a group here, we have a group here, and we have a group here. So there's 4 of these groups, right? So when we take the most frequent element, which is A, and we subtract 1, we get 4, right? Okay. Interesting observation. Now, when we do n plus 1, we get the size of each group, right? And that makes sense, right? Because n is how long we have to wait, right? So 2. We have to wait 2. We add 1 because we have to account for this A. So our size of our group is 3, okay? Okay, so there's 1, 2, 3. There's 4 groups. And each group is of size 3, okay? Interesting observation, okay? Now, max count is really the last group that isn't full. So it'd be this, right? But this could also be more than 1. Because, for example, if we had, let's say, 5 Bs, we would do 1, 2, these are bad Bs, sorry, 4. And we'd have a B here, right? So actually, max count would actually be 2 in cases where you basically have a tie in frequency for the most frequent characters or tasks, okay? And this will make sense, right? So this is basically our formula, given this, right? Because what we're really doing is we're counting how many groups are there, what is the size, and basically what is left over, okay? And that's basically how we're counting how many CPU intervals we have. Because we're laying it out like this, right? Like I said, we're using the most frequent characters. This is the most efficient way to basically use your task is to use the most frequent characters first, right? So that's kind of the gist of this formula here. Okay, is because you're building out like like visually we're building it out like this, right? But mathematically, this is how you would represent laying out your task like this. Okay. So we basically we calculate the number of full groups, multiply by their size, and then we add the number of most frequent tasks in the final group. And again, our most frequent task could technically be like this here does not, like, we're not adding one always. It could be 2 or 3 if we have cases where our most frequent character is tied. So if we had 5 A's but also 5 B's, we would add 2 technically here. Okay, so just keep that in mind. Okay. So, is this basically always going to be the case for a formula to count the minimum number of CPU intervals? The answer is no. Okay, because it could be just the length of the tasks that basically would give you the correct answer. And I have some examples to kind of illustrate that to you, right? Because really, what we're asking, this is basically cases where we have idle time, right? And this is cases where we don't. That's really what we're asking, right? Are we forced to have idle time or not, right? Because we could use B, C, B, C, right? So we use this, right? But now we have idle time, right? So, so do we have to use idle time or not? That's really the big question in terms of how do we find out what the correct answer is? Because this formula won't always work. And again, I have examples to illustrate this. Okay, so example 1, right? We have A with n is equal to 2, right? In this case, we have idle time, right? So we're gonna have to use this really, right? And how does this work? Okay, our max frequency is what? Well, it's just A, right? So, and how many A's do we have? We have 3 A's. So we do 3 minus 1, right? And n, what is n? 2. 2 plus 1, that's 3. Okay, and our max count is what? Our most frequent character is A, and it shows up how many times? It shows up 3 times. Okay, but what is our max count of our most frequent occurrence? It's just 1, right? What does that mean? It means our most frequent okay, what task shows up most frequent? A, and okay, and how many times does it show up? It shows up 3 times, right? How many different tasks or labels show up 3 times? Just 1, right? Which would be A. For example, if we had 3 B's here, the answer would be 2, right? What's our most frequent task? Well, it could be A or B, and how much does they show up? They show up 3 times. This here is basically us asking, okay, what is the character that shows up the most frequent? It could be A or B, and so it'd be how much? How much does it show up? It shows up 3 times. Okay, how many labels basically show up 3 times? That's what we're asking. And it'd be, how many labels show up 3 times, right? It'd be 2, right? A and B, they both show up 3 times. That's basically what this is. So don't get it confused. Max frequency and max count are slightly different. So I hope that illustrates the point. Okay, so we're going to calculate this, right? And we get 7. Okay, and that's what our answer should be, right? Because we have 1, 2, 3, 4, 5, 6, 7, right? So this minimum CPU interval time is 7. Okay. Now let's show you this case here. Let's see if I can. I'm gonna have to just zoom out a little so you can see this. There you go. Okay, this example here, we have 3 A's, 3 B's, 1 C, 1 D, and 1 E, and then n is equal to 2. Okay. Well, let's calculate this formula first, okay? Just to show you the point. So the max frequency is what? 3, right? N is equal to n plus 1, n is 2, so 2 plus 1 is 3, right? Sorry, I don't know if I said plus 1 for this. It is minus 1 for the formula for the max frequency. Sorry. So 3 minus 1 is 2. Okay. Because we're subtracting 1 here, not adding 1. So I apologize. What is our most frequent occurrence? Right, it is 3. Right, because A shows up 3 times, B shows up 3 times. So our most frequent occurrence is 3. right? So 3 minus 1 is 2, and n is 2, so 2 plus 1 is 3, right? So we have this. Now for max count, right? What is our most frequent occurrence? It's 3, and how many times does 3 show up? It shows up twice, right? Because we have A's and B's tied here. So max count is actually 2 in this case, right? So we do 2 times 3 plus 2, so 6 plus 2 is 8, okay? Now, how many tasks show up? 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, what is our minimum CPU interval time? The right answer is actually 9. I'll show you why, right? So if we set up our labels like this, right? Let's just use the A's, right? We have A, and then we have to have an interval time of 2. So boom, boom, A, boom, boom, and now another A. Okay. Now let's use the B's up, right? We have how many B's? We have 3, so we can do, we had a B here, we had a B here, and again, we trying to make it fit, right? We can't add a B here. We actually have to add it here, okay? And so we use 1, 2, 3, 1, 2, 3. Okay, now we have C, D, and E. So we had C here, we add a D here, and then we add a E here, right? That's how we use up all the tasks. Okay, now let's count this out. 1, 2, 3, 4, 5, 6, 7, 8, 9. The correct answer is actually 9. It is not 8, right? So you'll see this formula actually does work, but it won't work in cases where we basically don't have idle time, right? The length of task is actually what gives you the right time in these circumstances. So whether you use this formula or this formula is actually dependent on whether you have idle time. So this is actually the bigger number in this particular example, right? So in short, the best case, right? In the best case, we have no idle time. And in the worst case, we do have idle time, right? So we want to minimize the idle time, right? So in this case, we actually don't really have idle time. So the correct answer is actually 9, not 8. Okay. So let me go up here, right? So this is a formula that's important, right? So keep this in mind. Maybe I'll come back here in a little bit. All right, what's up, everyone? We're back in C++ land. So for this greedy approach, right, we're on the same problem as the one I just showed for the max heap approach. So same thing, right? We have these labels, but we don't have the frequency, so we actually have to count the amount of times each letter shows up. So we're going to use a hash map for that. So let's just do that really quickly, right? We're going to say unordered map, right? We're going to say char int, we're going to call it tmap. I mean, you can call it something else if you want. I'm just going to call it tmap, T for tasks, right? So we're going to say for char t task, right? We're going to say if basically when we're looking at these letters, if they already exist, just add 1 to the count. Otherwise, we have to set it to 1 if it's the first time we're encountering a particular key, right? So we're gonna say tmap dot find key not equal to tmap end. Right, if that's the case, we just +1, right? Because it already exists. Otherwise, I'm gonna set it to 1. Okay. I'm not gonna use braces, just using one-liners just to make my code a little bit cleaner. Okay. Right, just set up our hash map. And then we have max frequency, right, which initially is just gonna be 0. And we're basically gonna iterate through our hash maps. We're gonna say for auto. Remember, we have a key, which is task, the frequency, which is the values, right? And actually, we can use a one-liner here as well. So our max frequency is basically what shows up the most times, right? So we're basically just iterating through our hash map, grabbing which value shows up the most, right? If the A shows up 3 times and everything else shows up once, we're going to grab that 3. And we're going to store it here, okay? And then we have to do the max count. right? Let's just copy this because we're gonna iterate through the hash map again. Okay. Gonna iterate through the hash map again. Now the max count, remember, is basically counting. So whatever the max frequency is, like if it's a 3, how many times does that 3 show up, right? Because if we have 3 A's and 3 B's, the max count should be 2 because there's basically 2 letters that show up the most frequently, right? Because it's not always the case that the most, like example 1, what's the most frequent occurrence? It's 3, right? Either the A's or the B's. But how many times or how many letters show up 3 times? There's 2, which is what the max count is, right? It'd be 2. Okay, so the way we do this, basically, we already grabbed which one, what is the most frequency, which is 3. We already grabbed that and stored it in max frequency, right? This variable. So now we're going to iterate through the hash map again and basically look at these values. And if it's equals to max frequency, we're going to increment max count by 1, right? That's what we're going to do. So we're going to say if frequency is equals to max frequency, right? Then we do max count plus. Boom. Okay. Okay, and let me go back really quick, right? This is the formula, right? So we grab this, we have this. Now we already set this up. Now it's just a matter of knowing whether we do this first or this first, right? Okay. So the way we're gonna do this is basically the intuition is really whether we can fill the gaps or not, or whether we have to idle, right? Max int, right, task.size. And then here we have this is the formula, right? So we're gonna say max freq minus 1 times n plus 1 plus max count. Okay. I don't remember why I put this here. I'll be honest, I think I use AI to convert my code from Python to C++ because I was too lazy to write it out myself. I was just trying to get over this problem. No matching function for call to max. Cast it. Oh yeah. So yeah, I guess you do have to cast it. I don't remember why you had to cast it. Let me see. Oh, right, because this is an unsigned int, I believe. And this is an int, and to compare these, they have to be the same type. Because task.size returns an unsigned integer or an unsigned type. So yeah, just C++ semantics, syntax stuff. Be honest, I'm not the biggest C++ user, not the smartest C++ user. So if you knew the answer to that, you are smarter than me, my friend. But yeah, this is a weird problem. So yeah, definitely one of the more difficult ones I've ever done. Yeah, I mean, if you could solve this by yourself, honestly, I really applaud you because I think this problem was pretty dang hard. Yeah, I hope you understood. Like I said, I was editing some explanations and illustrations for my Python video, so hopefully you're not too confused. Hopefully you understand at least somewhat why we're doing the things we're doing. But yeah, I hope this helped, and I'll see you in the next one. Peace out, my friends.